Morning everyone. You are getting harder and harder to attending the class, especially running and low temperature. And I will encourage you guys to still attending the class because we haven't been using Kahoot or Zoom here for a while. So we suspect maybe the rest of the week we will have some interaction. But anyway, if you really have a trouble attending the class, there's always NTU Cool for you to study. Then, yeah, and that's it. So before we enter chapter 3, we still have one section left, is the heat generation in the different coordinates. And that one is relatively important if you really want to know what's happening when things get heated up and the temperature distribution and the cube are going to transfer. So we are going to address that. But before that, I will take something slightly simple topic to sum up the section before 2.5. So as you recall last week, not the last week midterm, but the last week lecture. So when we're dealing with the constant coordinate, then we said there's a wall and then you have a temperature distribution along the thickness of the wall. And it turns out applying the governing equation of the heat equation, then you by separating the deviation, then you are able to find out the constant 1 and constant 2, and then you have a full temperature profile at here. So as you can see, that's the temperature profile. And similarly to the cylinder coordinate, then you can do the similar things, and with getting this kind of temperature profile in the cylinder coordinate. Then, as you remind in the fluid dynamic, the one thing we love to do is make everything dimensional analysis, which you are able to compare different kind of situation. For example, we will put U divided by the bigger U, then we put it into U star, right? Then in some of the length comparison, we put X and divide by, for example, L, then we get X star. That's quite similar in the fluid dynamic because those questions might be complicated. So using the dimensional analysis allows you to do the comparison between different phenomena and different scale, different size. In the heat transfer, it's also very important to do the similarity comparison and also dimensional analysis. So the first thing we are going to do today is to show you the dimensional analysis, and later on, from this dimension analysis, we'll introduce a relative important, or no, I won't say relative important, the most important dimensional number, non-dimensional number in heat transfer. The importance is equal to Reynolds number in fluid dynamic. So that's things we're going to, before we enter into the heat generation in different coordinate. Okay, so in the constant coordinate, then if we want to write this equation in the dimensional form, then it should be quite easy. So the dimensional forms will be the place you want to know for the temperature minus one side of the wall and the temperature difference, okay? Should be alright. And this, according to the equation at the front, that will become the X divided by L. So that's the temperature dimensional analysis in constant coordinate. And for the spherical, it's also the same. We do it again. So the temperature in the R, I want to know, divided by the either outside or inside, then the temperature difference, B should be B, divided by A. And if you do the calculation, that would become, that would be need to write separately. This. Oh, no. Okay, so this will be the dimensional analysis of the cylinder coordinate. For the spherical, usually we won't do that, but if you're interested in, you can try to do it in spherical system. But as you can see in our previous lecture, the temperature profile is slightly complicated. So you need to move around and then divide something and times something to get those numbers. It is relatively used, so if you like, then you can still do it. I'm only just show you the concept of the custom coordinate and the cylinder coordinate. Okay, so once we have this, I would like to introduce the most important parameter in the heat transfer. Okay, the most important parameter we probably already mentioned a little bit, compare with the fluid dynamic, is Reynolds number. In heat transfer we call Field number. 比尔数，中文如果要翻译的话，那不同课本可能会不太一样。So in the Reynolds number is the comparison between inertial force and the viscosity force, and Beer number is also a comparison between something. So this is the comparison between conduction and convection. Okay, so the thing to judge a thing, the ability to handle or to propagate the heat, either by dominate by conduction or dominate by the convection. 好，我们如果要衡量一个东西，它是传导比较多还是对流比较多的时候，我们会用比尔数来去做判断。那为什么这件事情重要呢？因为当 if the conduction is really, really huge, which means it approaching to a steady state, so a lot of system can be simplified. 好，所以这个东西就很重要。那你的计算上面甚至也可以不用考虑 convection， 因为 convection 很少。但反之，如果比尔数很小的话，你就是一定要考虑 convection. So now we take an example. Well, then we have the x and t graph. And let me draw a wall. Okay, that's something we already mentioned in previous study. So there's a temperature on the wall. We call T0 or T outside. Then another side of the wall, we do have the convection because we want to compare the convection, right? So we must have convection. And convection, then we will have H. And the temperature far, far, far away, okay? And the thickness of the wall or the material is L. Okay, that's quite similar. We have been talking about this example for a long while. Okay, so first things, we still writing down the governing equation. So the temperature distribution will be this. This is the most simple one. Okay, then start again applying the boundary condition. So when the x equals 0, the t will become TO. Okay. Then this is at this surface. Okay. Oh, that's a very big one. Okay. So on the left-hand side is it's not pure conduction. This is only a boundary condition or inertial condition tell you the surface has a temperature called T0. Then if we consider another side of the wall, then here have a phenomenon with conduction and convection. Okay, so which means that how the heat going to propagate will become, the Q will be the same. So let's write it down like this. Equals to H and T x equals to L minus the temperature far away. Okay. Okay, so this is on the right hand side, and this is on the left hand side. So those are the boundary conditions we have right now. So then we can solve the equation. So on the governing equation. So I won't go into the details. So I just write it down. The answer. You should be able to walk around. HL, and it's very easy to remember. And the C2 will become like this. Okay, so when you put C2 into your governing equation, when you put 0 into your governing equation, then the Tx equals to T0, and they put it back to the orange one equation, then you got C1. Okay, that's easy. Okay, so now the temperature distribution will look like this. So let's write it down. Too much. K plus H. Okay. Okay. So now we need to put a little bit play and to trick the equation into the dimensional analysis. As I mentioned like 10 minutes ago, usually if we see something with the dimension of length, then we are trying to put it out together, for example, x, then we want to make it dimensionless. So let's do it like this. So we divide the k and L and try to make it. So let me directly apply for it. So H, L, K. Because we want to get rid of the K in the front. It would be easier. Here will become 1. Let me write it down like this. The later term will remain the same. But here become put in blue. Okay, in that form, in this sense, the equation, now we already have an x start. That's the dimensional analysis. Okay, now by looking at this new equation, you might find something keep repeating. This one, HL divided by K. Let me highlight it. This one. So this must be something quite important. It seems like forming a ratio between the temperature difference. For example, now it's the temperature dimensional analysis versus the geometry dimensional analysis. Okay? If you put Tx, TL minor and divide this, so this term will be the temperature difference. This will be the size difference. And there has a function how to express that using this kind of term. So which means this is very important, and this is the one we're going to introduce today, Beer number. So this is Beer number. Let me write down in red. Okay, so Beer number, like Reynolds number, then defined as the convection coefficient times the characteristic length and divided by conduction coefficient. And I would like to remind you, the K here must be solid. because in the fluid, in later chapter 4, we are going to introduce a K specifically using in fluid. So the equation will be that's for alert, exactly the same. But this is fluid. This we call Newton number. I will describe later, but now just remember real number, the K is in the solid. Okay? Let me erase this one. I'll describe later chapter. Okay? So what is this for? As I mentioned, so the real number is to judge something or a situation. You want to judge the intensive way, which conduction or convection is more intensive or more dominant in certain, certain object or different scenario. So you use the real number to do this kind of judge. So this is really like the Reynolds number from the Navier-Stokes equation. So if you want me to remind you again, so in the fluid dynamic, that's right, FD. So something you need to judge is look like this. So as well, in the fluid dynamic, you also make your velocity become a V star or U star, depends on the textbook. And there's a Reynolds number also function in the front. So that's something to show you if the Reynolds number is really, really huge, which means the viscosity force didn't dominate the situation. Okay, because the Reynolds number is at the downside. Okay, so it's quite similar to the fluid dynamic. We keep saying that because later on we will go to compare the fluid dynamic behavior to the heat transfer, because heat transfer is more complicated than the fluid dynamic. So some of the situation we cannot measure the temperature. We won't know how many Q or what's the temperature distribution. So we can use the velocity distribution to guess what's the temperature distribution in the heat transfer problem. Okay, so that's the analog, Reynolds analog. So I will show you later. Okay, so we just give you some conclusion. So if the real number, usually we put it into the BI, is less than 1, then which means we have less convection. Okay, then if real number bigger than 1, much bigger, it's not 1.1. Okay, so which means that we have more convection. Okay, then if we put it into more detail, so if the real number less than 1 or much less than 1, which means Tx is roughly equals to what? TO on the surface. Okay? Then which means the convection didn't have really have an ability to get rid of the heat. Right, like on the right hand side, the orange part. Okay. Then if you try to draw this figure, the T and X figure, like this, then the velocity the temperature profile, TO, and this is T, surface, then the temperature profile will be something like relative change, then compare with the straight line. It only changes a little bit. Okay. Okay. Then what if the real number is quite huge? Then which means the equation will become Tx T infinity minus TO and XL. Then keep everything here. Okay, so because we put infinity here, then it will become 1. Okay, so the equation will stop here. So the temperature distribution will become only this part. Okay, so this is implied. The whole system becomes steady state. Then this will make things from PDE to ODE. So use the Beer number to check your problem. As long as the Beer number much bigger than 1, then you don't need to solve the PDE. It must be a boundary condition, an initial condition for you to simplify the equation and become the ODE equation. Okay, and the physical meaning is the Beer number is really huge, so which means the heat comes in to the wall and immediately bring out on the origin side. Okay, so there's a steady state. There's no such temperature like a nonlinear behavior inside. So the temperature profile become linear. 就变成接近稳态，你的热一进来就被带走，所以它穿透的能力非常好，不是穿透能力，传导的能力非常好，所以它一定会是线性的，所以我才讲可以从原本的 heat equation 它是一个 PDE 嘛，直接变成 ODE， 其实就是我们上个礼拜在解的东西，为什么它会是一个线性的东西 ？OK， 那你如果从 equation 来讲，你要从头到尾推，然后你就说啊，这个是线性的。但是今天 Beer number 就是说你在任何研究上遇到了这个问题，我拿来 Beer number 先比了之后，它只要远大于1，我就是直接把它当成你手边可能知道的 boundary condition 就放进去，你就不要想说啊，这个假设会不会有什么问题？不会，因为它就是变成 ODE steady state， 我们就可以用 steady state 的方式去解它，会很趋近于正确的答案。Then this kind of system is also called lump system。这个我们就会称为云团系统。它的物体里面的 temperature distribution 是相对来讲稳定的，或是它的 temperature 的变化是线性的，你是非常好解的，或是它把它当成是一个常数，因为应该说线性也可以是 T 直接等于一个温度，或是 T 等于一个什么关系式这样子，所以如果你做这样子的判断，你就可以简化你的东西。所以 Beer number 这件事非常的重要。如果你不知道 Beer number 的话，你就变成你从头到尾要去做求解，那这件事情呢就很令人头痛。Okay? So if you guys are okay for that, we will move to the last section of the chapter 2. And for chapter 2, you might think it's a lot of math, but in the chapter 3, that everything will become very simple, because chapter 2 is dealing with the TDE and making ODE, then we do the integration, blah blah blah. But in the chapter 3, that's only elementary school. It's only plus, minus, divide, and times. Because we don't care about the temperature distribution in the object. We only care about what's the temperature on the surface, on the end. 所以第3章会非常简单，所以我们速度非常快，所以我们重点会先放在第2章，然后跟第4章。第3章非常的简单，因为它是电路学的概念去来解释这件事情。Okay, so any questions on Beer number? If no, I will move to the heat generation part. Okay, if it's no, then there will be easier for me to pull the prepared notes directly to you. Okay, that's the prepared note for me. Okay, let's start with that. So we talked about the heat generation in the different chronogenates, and there's still some assumption. The heat generation is uniform. I will give you these slides. No worry. Just follow me with those equations. Okay, because only for the people who would like to study in the thermofluidic group, then you probably need to solve this question. So for the rest of you guys, just know how to solve using the rest of the answer and then try to pass the class. Okay. Okay. So assumption is steady state and the K remain constant. And we have heat generation. That's different from what we talked about in the 2.5. But the heat generation is uniform. It could be ununiform. It could be transition. But we can address this. But it's too much math. And we also can address if the K is non-constant. That will be 2.7. So if you guys are interested, you can study on your own. But if you insist I record a video, I can do that for you as well. Okay, but similar, we start with the heat equation. Okay, so start with the heat equation, generally equation. So let me remind you, if it's a plate, it's a plant, so the N will equal to 1. If it's a cylinder, the N will equal to 2. For if it's a spherical, then the N equal to 3. Okay, so this is the heat equation. So this time we didn't eliminate the Q generation, but it is a steady state, so the time term is also eliminated. Okay? So for the constant coordinate, for example, that's a plate, then the N equal to 0. Sorry, I correct myself. So yeah, just move a little bit. Okay. So then it's a plate, so we put the R become X. Okay, it's similar to the one we have. So the equation will become like this. So you draw this plate, their heat generation in the middle. So for the easier to say, we put it into a symmetric system. So there's a central line, the thickness is 2R, one is minus R, one is minus L and L. And heat generation, then you have a temperature on the two surfaces. Then we do the similar things, we do the integration and find out the first constant, C1, and I'll do the second. Then we got a temperature profile with two constants here. Okay. Then by looking at the equation, you found there's a square here. So which means the form is like a parabolic profile. Oh, things that note written is in Mandarin, so this is parabolic. So it's something with this. Okay. Then it matches something when we start talking about the boundary condition and initial condition, if you remember this one. Okay. You have the surface temperature on both sides. You have a heat generation. The temperature distribution inside of the object must be parabolic. Okay. And remind you, in the fluid dynamic again, this is quite similar with fluid development flow between two plates. Okay. That's a two plate. Then that's a flow. Then you have a parabolic profile. So fluid dynamic again. Then you written down your velocity profile in this form. So this is also parabolic profile, C1, Y, C2. So it's really, really similar to each other. So which means if you don't know the Q generation, then you can use the pressure drop to simulate, and the mu will equal to K. So later, if you have something very complex system, then you can use the fluid dynamic to solve it, because the fluid dynamic is well developed. There's a lot of equation to solve it, but not in the heat transfer, especially heat transfer combined with the flowing liquid. It's very complex, but we can similarity this one using the fluid dynamic. Okay, so far so good. Okay, so start something again. If you want to know what's the C1 and C2, apply the boundary condition. So when the x equal to minus L, the T will equal to T1 on the surface, and the x equal to L, T equals T2 on the another surface. And when you put it back, to the equation, then you got two new equations look like this. Slightly complicated, but then you assign it as a question 1, equation 2, and question 2 minus question 1, get rid of C2. Then you have a relationship of the C1, and then you can easily have it. Then if you combine the equation 1 to equation 2, then you got C2. Okay. Some of the students still want to take a note, so let me put it a little bit. And I guess you can also use the screenshot to have the note back to your home. Okay. Then we put it back, the C1 and C2. Then we have a full heat equation. Oh, no, not heat equation. The velocity the temperature distribution in this kind of heat generation style. Then some of the students were already noticed. Here we have a dimensional analysis of length. Then you can put it into the C start. Then if you like, then you can do some rearrangement to let the system become sum of the temperature minus 2 the temperature I would like to know equals the temperature difference. Then there will be a relationship of something. You can do this kind of a dimensional analysis by yourself. Okay. And typically in this kind of question, you have the heat generation inside of your solid. The typical question will be, so where is the maximum temperature? So the maximum temperature, we already talked quite a lot. The maximum temperature will be only achieved at derivative T divided by derivative X equal to 0. 我的最大温度一定会出现在底 T 底 X 等于0的地方，因为它是抛物线的折返点，那它一定会是最大的地方，也就是 this point. So the slope will become 0. Okay. So the slope at this point will become 0. So that's the boundary condition to find out the maximum temperature. So in this case, then we have another boundary condition here. Okay, so blah blah blah, then you have this, and then you can directly jump to heat. So the T max will at the X equals to 0. I mean, if you don't believe me with this kind of a physical observation, then you can start with the boundary condition to drive your equation again. Then you can still find the T max. Okay, so the T max will definitely at the center position. So the T max will equal to Q generation times the L square and by 2K plus Ts. Okay. So let me back to note. So let's have an example. We have a wall. Then the left-hand side is insulated. Insulated wall. So which means there's no heat flux in this direction. And we have something heated here. So that's the heat generation in the middle. Okay, Q generation. And here we have convection, H. And the thickness of the things is L. So for example, this is a refrigerator put against the wall, and there's a air condition or the fan have a moving liquid. So this is Tx system. So let me write it down, the equation we just derived. So the Tx will equals to minus Q 2K x squared plus C1x plus C2. Okay, so we apply the boundary condition very quickly. On the left-hand side, will be isolate. So minus k dt. Okay. X equals to 0. And another boundary condition will be minus k dk dx. X equals to L, will equals to what I'm going to take out the heat by convection. Okay, so the T X equal to L minus the far away temperature. And that's the boundary condition we have right now. Okay, so we put it back the X equals to 0 to the upper equation. Then you can easily get the C1 equals to 0. Hi. And the C2 will equal to Q generation plus L, then move a little bit, H, and 2K, love it, Q generation, L squared, plus far away temperature. Okay, then try to put it back C1 and C2 into an equation, then there will be something in this case. If you have a heat generation and you have an insulated wall and on the other side, so which means the surface temperature on this side, T in and T out, is different. Okay, it's not necessary the parabolic flight asymmetric. Sometimes asymmetric because the heat won't distribute at both directions. Okay? Then if you want to know what's the parabolic inside of the object, then you use this equation, this one. 好，它虽然是对称的，应该说它不是对称，它虽然是它虽然是抛物线，但它不会像我们刚刚讲它是对称的，因为那个完全对称的 case 是两边都没有东西，然后两边都有对流，或是两边都是 insulate wall， 那你一定会是对称，那你 maxima 一定会在正中间。但如果今天这是一个不平均的状态，你旁边是 insulate wall， 右边是 convection 的时候，你还是会是 parabolic， 但这个 parabolic 就不会是对称的，还是会有一点斜斜的。那这个 parabolic 长什么样子呢？就是用这个方式解。OK， 你这个地方 x 等于0的地方，你绝热的，所以这个地方热传等于0，你左边的握热传等于0，你右边的握是 conduction 等于 convection， 用这样子的方式呢带回去我们的 heat generation equation 就可以得到这个 parabolic profile。好，那我们没算不知道长什么样子，说不定外面的风是很热的，然后 temperature 是往上走，也有可能是长这样子的 parabolic profile。那一样，它的 maxima 也是令它等于 dt dx 等于0的那个位置，一定就是 maxima。好，斜率等于0的位置，但不一定会在正中间，这样可以吗？好，我们先讲到平板位置，然后之后我会给你一个 general solution， 任何 shape 中间有发热的，都可以用无因次的方式去处理这件事情，所以我们会讲求圆柱，然后接下来讲几何形状很复杂的这样。好，那我们今天先花一点点时间来介绍一下东京理科大学的上野一郎教授。那上野一郎教授是东京理科大学机械系，然后也是热流的专家。那他擅长的东西呢是相变化，但是我们现在还没讲到，但是大家可以用高中的 idea 去想那个相变化就是 phase change， 然后 you have latent heat， then how the phase change will affect and how many heat is going to transfer because the most bigger edge will be appear in the phase change， 就是 h 的这个值呢，只有在相变化的时候它的值，其他的值都是100以下，但相变化的值会到10万、100万等级，所以就表示只要东西有相变化，它的热传效果就会非常好。所以上野一郎老师他就是 working on this subject， 然后这个东西呢，同时间他也跟日本的 JAXA 合作，然后因为在太空当中的这个散热非常的tricky。你要换一个那个 ？Okay, so we got all the three. Then the stage is yours. Do you need to use here? Yeah, sure, of course. That's a microphone. Thank you. So let's give applause to Professor Bueno.
Good morning. It's a great privilege to be here. I'm kindly invited by Professor Chiang to start some collaboration in terms of heat transfer engineering and also heating program. Okay, today I'd like to share you some time to introduce the boiling phenomena, topic of heat transfer engineering. So I just checked this morning the online dictionary, Fate.
That's very kind of you.
Fate 10. So it's a very tough one. But okay, if you check the dictionary in English version, so it's a very common and also a very popular phenomenon in your daily life. So we have phase change from liquid to vapor with abrupt change in terms of density, so that we have a big change of volume by the phase change process. Okay, just Professor Chiang introduced the heat transfer coefficient. So if you plot heat transfer coefficient in horizontal axis, then, sorry, I don't have. Okay, have you already learned free convection heat transfer?
We introduced, but we haven't moved into the equation phase.
Okay, got it. So in terms of free convection, okay, if you put heat and to increase the temperature of the fluid, the density is a function of temperature. And if your fluid get heat, then the density becomes less, so that thanks to the gravitational acceleration, you have motion of the fluid, so due to the difference of density. Okay, and also we have forced convection, like using hand fan, for example. So this is another example of forced convection. So you have a thin structure here, then you enhance the heat transfer between the ambient fluid and heat from the engine. Okay. Then, as she mentioned, the body heat transfer has great benefit from latent heat. I don't know how to pronounce in Thai language, but thanks to the latent heat, heat transfer coefficient of boiling become much higher than free convection or forced convection. So this is the topic. And then, okay, let me introduce some movie. This is a movie given by a group of Holland. Do you know?
Yeah.
Okay, yeah, that's right. So I think this is a great example to see or to observe what happens in your kettle. Okay, you prepare a heater here, and you prepare ethanol instead of water, because very small latent heat compared to water. Before boiling start, okay, let's see. We have natural convection without boiling. Okay. Do you see some fluctuation of grid? I think this is a very popular phenomenon when you walk on very hot summer days. Okay, then, due to temperature distribution, non-uniform temperature distribution within the liquid, then diffraction become different due to temperature difference. Okay, then you could, this is good. Okay, then you can visualize the temperature distribution within the liquid. So let's see. So this is a heater, and this is your ethanol. So as I mentioned, if you put heat from heater, so density near the heater become less. So lighter fluid exists below the heavy fluid. Then you have a natural convection. Then, as you can imagine, the hotter fluid or lighter fluid go up thanks to the gravitational acceleration. But as you see, we don't have, can say, the homogeneous rising up behavior. So because of so-called Rayleigh-Taylor instability in terms of fluid mechanics. Okay, then if you increase the power of heat, then you can see the boiling instead of natural convection. Okay, see, so this is a very typical behavior, as you see. And if you put the, I forgot the name, liquid crystal, liquid crystal, then you can visualize the bubble motion. And as you see in a natural convection, we don't have homogeneous rising up behavior because of Rayleigh-Taylor instability. And this is a very dangerous situation for you if you work at the industry. So this is so-called film boiling. The situation is the temperature of the substrate is too high for the liquid to touch the substrate. So that heat transfer between the liquid, between the liquid and heater comes from radiation through the interface instead of sensitivity. So this is very dangerous situation, as I mentioned. Then heat transfer surface is covered by vapor film. Then this is end of okay, we have a different application of boiling phenomenon even these days, even now. So there are so many applications and also so many things to be investigated. Okay, the major purposes of boiling phenomena is vapor generation. This is one of the most popular ones. It can be applied to a boiler, for example, and also air conditioning system. It cannot survive in and also, this is what I have been interested in, boiling cooling effect. So, okay, if you hear boiling, the word boiling, it can be meaning heating, but instead of heating, we can apply the boiling phenomenon for cooling technology. And I'm going to do this later. And this is, I think, not popular purpose of a boiling application. So if you print some your report to your presentation, if you use inkjet printer,
They are no longer using inkjet printers.
okay, that's right. Okay,
沉
I'm
默是印表机，你们现在没听过都是镭射印表机，镭射 printer。
I came from previous century, but so I'm too old. Okay, I'm going to skip this. And okay, so in order to understand, apply the boiling phenomenon, so you have to understand these topics. So you need to deliver the cool or low temperature liquid to your heating. So you have to control these kind of things. And these are the applications fuel cell or electric vehicle. And in the near future, we're going to apply to boiling heat transfer technology to living in microgravity or low gravity condition for environmental control. So sorry for taking a long time. Okay, that's all. Thanks so much for paying attention.
Thank you, Professor Ueno. Since he's visiting during the August, unfortunately we cannot touch to the boiling just before that, but you guys should have an idea when there's a film building up on the heat surface, because the gas is more insulated by the water, so the heat cannot propagate directly through the bubble, then the heat will accumulate on the surface and then just damage the electronic device on the surface, etc. So how to get rid of the film, or just increase the mass, the Q, the heat flux, then that's the thing the current scientist is working on. Yeah, so if you guys are interested, we'll also propose something in NTU, and actually a lot of professors in NTU are working on this topic. So if you guys are interested in, maybe we do have some, I don't know, student able to exchange to his university to do some short-term research. So if you guys are interested, please write me an email and reach me. Then we can set up this kind of internship. Okay, thank you very much. And so let's give a applause to Professor Ueno and the class.